thanks. So I'm trying to be fast because I know some people want to catch the shuttle, and we're already a bit behind. So I'm going back to the S stars now, so making a big bow from the first talks that we heard today. And this is work I did a couple of years back, well, a year or two back, when I was still in Leiden, and I was working with Simon and Edwin van der Helm and Inti Pelopessi. And as the title suggests, it's about the wind of the S stars and the accretion onto the black hole. So I don't have to, introduce you to the S stars again. We all heard about them today. We have these clusters of stars in the galactic center which interact directly with the black hole. So this is a very, very nice laboratory to probe how winds of stars actually interact with the black hole and contribute to the accretion to the black hole. So our goal was here to basically, there we go, to simulate accretion from the stellar winds onto the supermassive black hole. Was the whole goal of the project. We wanted to see how much do these winds actually contribute to the accretion of the black hole. Can we explain the whole accretion just with those winds, or is it completely different? So this is the setup we used. It's a very generic setup, and I'm coming to the choices we made there later. But yeah, that's how we started up. And then, of course, if you want to simulate this, you need to combine a lot of physics. You need to combine gas and gravity and also stellar evolution. And the best way to do this is AMUSE. That's the Astrophysical Multipurpose Software Environment. And I'm sure Simon will tell you more about this on Friday. But for everybody who wants to make a simulation that has more than one specific physics in it, or even just one physics, I can highly recommend AMUSE. AMUSE gives you an interface to communicate with codes that have been written for years and years in different languages, in Fortran, in Python, or in C++, and makes them talk to each other. And as the user, you can just write a Python script. I mean, it sounds easier than it is, and let these codes basically interact with each other. So I would highly recommend, if you're interested in this, look at the website. There's going to be a book coming out very soon. Again, Simon will tell you about that. I didn't find the book cover yet, so it's not published yet, but it will be there soon. So in our case, what we wanted to do, we needed basically all of these modules there. But since when I started, the radiative transfer was still a little bit in a beta version, I only used those 3 modules to make my code. So hydrodynamics, gravitational dynamics, and stellar evolution. So to introduce you real quick to those codes, this is probably outdated because MUSE is growing and growing every day, so there's more and more codes added every day. But here's the codes we used, and this is the stellar evolution code. In principle, we didn't really need stellar evolution because we ran our code in a very short time scale. But in case you want to run it for longer, we thought we'd bring it in because it wasn't really hard to actually put it in. So we use SSE, which is a parametricized code. And but you can actually exchange it for other codes if you want to see if there's different effects from those codes. The next thing is the gravitational dynamics, of course. AMUSE has tons of different gravity codes, n-body codes, but also tree codes, Kepler codes that you can choose from depending on what your project is actually about. So you can choose the best code for this. And we used PH4, which is kind of like the AMUSE workhorse for gravitational codes. And then last but not least, the most important one, if you want to simulate stellar winds, we had to use gas. And here I was using Phi or Phi, or however you want to call it, which is an SPH code. And this is a simulation by Inti Pelopessi. He was the one who developed this code. And it was very nice for me having him basically in the same office when I was there so that he could help me with that code. So now if you want to bring all of these codes together, there is another really important part that is still missing, and that is called bridge. And bridge is connecting the gas dynamics, for example, with the gravitational dynamics. So it makes the gas actually be self-gravitative and feel the gravity of the other systems in your simulation. So and if you, the next simulation shows 2 cases, one where bridge was actually working properly, and one where bridge was not working. And I actually made the simulations and looked at them and realized that something was wrong. So here on this side, you see it's a star with a stellar wind going around the black hole, very simplistic. And you see here, this is all going well because the gas is actually feeling the gravity. It's going around the black hole with the star. It stays around the black hole. And on the other side, the gas doesn't care about gravity at all. It just puffs away in little puffs. And you can pretty quickly see that your simulation is not working well yet. Your bridge is not linking those 2 components. So bridge is very important for our simulations. then how did we do the wind? It's actually in a very simplistic way, because all we wanted to have is just gas coming out of stars. We were not interested in the intrinsic wind properties. But AMUSE actually has a very, very nice wind module, so you can simulate stellar winds in all their complexity, or as complex as you want to do it, with pressure gradients and all of those things. So in our case, all we did for each time step, we distributed our gas particles around our star. We gave them a temperature, which is very similar to the effective temperature of the star. And we gave them an outwards velocity, which is equal to the final velocity. And this, again, depends on the parameters of the star. So our stellar evolution code would tell us what is the mass loss. So that determines how many of those particles we need, and what are the stellar parameters. And depending on this, we created wind. And then we let the SPH code do the rest. And this is how it looks at the end. It's a stellar wind. It's very zoomed in, so it's quite clumpy. But that's all we needed. So now we put stellar wind and all of these components together, and we put stellar winds on stars and let them go around black holes. And at first, we just used all of our S stars, and we let them go around the black hole by themselves. No, they don't have spin. So we let them go around the black hole and see what the different orbits actually do to the accretion of the black holes. You see this is obviously S2 going crazy over there. And then you have all these different orbits. We have spherical orbits or more eccentric orbits. And no, we don't. Yeah, that's something that we might want to add in the future. There's a lot of other things that would flow in, probably, which we have not considered in the simulations. It was solely. So this is star by star. We did several simulations. We first looked at star by star, and we looked at what's the accretion from each star, and then we put them all together. I usually save that video for the end, because it's always a very nice thing to look at. But right now, it's more important to show you what kind of simulations we did. So this is all of the stars together. You see it's very violent, very clumpy. And I'm coming to this clumps in a second. And very hot. It's a very hot environment. We tried cooling, but our cooling time scales were way too long, so that didn't work. So it was still very hot, which was actually not so far from the observations. And yeah, this is just showing you the three-dimensional list of this whole thing. And I think we can go on with that. So as I said, we looked at the stars individually first and see which of the stars would actually contribute most to the accretion. And surprisingly, it wasn't S2, it was actually S14. S14 gets closer. And then we looked, so this is like the individual stars. Yeah, in this case, they are separate. And now I'm comparing. So this is for all of them separate. And I'm just adding up the accretion. And then I made another calculation, like the video I showed you afterwards. And so where we put them all together. So this is, I wanted to compare, is there a difference between having them separately and summing everything up, or putting them all together? And there's a difference. So when I have them all together, I get a higher accretion than the sum of the individual accretion stars. Which is probably because now we have a deeper potential in this case, because we were simulating this all pretty much in isolation. But there's so much chaotic movement going on in there. It was a bit hard to pinpoint down why we got so much higher accretion when they're all together. And then, yeah, there were many reasons why this could have happened. But we wouldn't have been surprised if it would have been the other way around either. So we were like, well, OK, there we go. That's apparently how it goes. And then this is just like, I was trying to find a correlation between the most contributing stars and their orbital parameters, and I was hoping I find a bit more strongly correlations here. This is basically the contribution as a function of the pericenter distance of the stars. And you can see S14 is falling very well, and this correlation comes closest. But then it's weird that, for example, S18 is so high, because it's actually not coming that close. So there's more parameters actually playing a role in this contribution.
How different are the wind properties of all these?
And they're all the same, because in this case, we all gave them the same parameters. They all had, and that's the simulation where they all had, were all 9 mega years old and 20 solar masses. The radius was at 100 AU. I have some, sorry, I had some slides where I was explaining why we wanted to use 100 AU. But yeah, our accretion radius is 100 AU. So it's basically the closest what any of those stars comes in.
Why did you choose
next slide. So, well, different masses between the stars. No, we didn't do that. We didn't go that step because at this point I was not really sure what were the masses of the individual stars. So, in this case, we were just varying masses of all of the stars. So this is what we were interested in. That's the accretion. So that's a cumulative accretion over our 500 years that we simulated it. And the gray area is what we found in the literature, measurements in accretion of Sagittarius A star. And the green line is what we found with our current setting of the 9 megayears and 20 solar masses stars. And then I thought, let's change the parameters and see what happens. And I was actually surprised that it changed the whole accretion by so much by just changing our stellar parameters by a few digits. And this is all the runs we did. So you see, we made the stars a bit younger, and we made them a bit less massive or more massive. And with this, we got all these different accretion rates. And we were actually a bit puzzled by that the accretion rates got so different by just changing the parameters by so little. So at the beginning, we thought, like, oh, this is cool. Maybe we can basically give some constraints on the stars based on the accretion rate. But then we looked a little bit closer.
Is that years or megayears?
Years. That's just over 500 years.
So if you allow it to go for several million years, even that slope would be much higher.
Yeah, that's true. But we have different slopes in those guys. I think this one might have been the same as the observations. It looks pretty much similar. But yeah, that would have been higher. It's the accumulated. Yeah. That's what we found in the literature and values. We just used that to show that on the cumulative plot. I think it's 10 to the minus.
Accretion rate from the literature and just let it evolve.
Yeah, no, I just overplotted the accretion rate of the literature with ours. Yeah, in principle, yes, I'm taking the accretion rate and let it evolve.
Why does it turn down? Then it evolves again. I just don't understand calculation of mass. As they continue to lose mass, it either builds up the density, or it gets accreted, or it gets blown out of the system. What's happening?
Well, we also remove gas from the system. When it goes away, I'm not considering it anymore.
You remove it by hand?
Yeah, I remove it by its velocity, if it has a certain escape velocity, or by distance. I remove the gas particles.
Have you reached some sort of inflow-outflow solution in the thermalized wind materials by the end of 500 years?
What exactly do you mean? With like?
You have some steady flow out and some steady flow
Yeah,
in.
pretty much. Yeah. Yeah, I mean, you see it flattening out. It's kind of starting to accumulate. Yeah, I'm sorry. I think sometimes people get confused with that plot. With the thermodynamics? Yes, we tried to cool it. It didn't really work. We had line cooling, but the cooling time scales were way too long, so it didn't really change anything in our temperatures. Yeah. Yeah, it gets heated like crazy by at 10 to the 7 Kelvin, something like this. But I compared it with observations, and it wasn't that far off from that. So yeah. Anyway, so we wanted to find out why we had those different accretion rates in the first place. So we went back and looked at our stellar evolution code. And here you see that what the stellar evolution code gives you as a mass loss rate as a function of time for different stellar masses. And you can see all these jumps up there. This is when the star is highly evolved, becomes like a Wolf-Rayet star, and starts blowing out wind like crazy. And unfortunately, now looking back what we actually simulated, we found out that two of our stars were actually two of our simulations were the stars that were highly evolved in this case. So the green and the yellow, the highest accretion rates, were those ones which had crazy winds. So now we know that the S stars do not look like this. We know they are not evolved. They are B stars, they're main sequence stars. So we could actually, after looking at this, pretty much exclude those guys. And then we were left basically with only the lower accretion rates down here. So our conclusion after this whole confusion about this was, no, the S stars do not explain the accretion rate of a Sagittarius is A star by themselves. At the end,
Waited longer, it might have just built up because that gas has to go somewhere.
yeah, but it's the accretion rate that is observed is a certain. I mean, I didn't just look at the cumulative. I looked really at the accretion rate, so over time. I just didn't plot it because it's very noisy. So we were always magnitudes below the accretion rates, like solar mass per year kind of thing that came from the literature. So that just showed the plot to see where we are.
But your orders of magnitude too short in time.
Yeah, but we have an accretion rate, which is per year, right? This is measured, and I can measure that from my simulations. And I know we went in kind of a steady state, so we knew that wasn't.
Yeah, I think we should simulate at least as long as the orbital time select 1 year radius or something like that.
Yes.
It's longer than 500 years.
Okay, yeah, we should have simulated it longer, but they also got really, really slow at the end because we were adding, well, we had a steady state at the end, but then we had a lot of particles in your simulation, so we couldn't go that much further with the computers that we had. But yeah, definitely something we could think about for the future. So in the last couple of seconds, I wanted to quickly talk about those clumps because people were always looking at those clumps and say like, hey, could this be G2? Could that be a G2-like object? You have so many clumps. Do they look like G2? And so I wanted just to see whether or not I believe what G2 is, what those clumps could be, and if they could actually look like G2. I have to put some caution here. We used SPH, and SPH likes to clump. So some of these clumps might not be, or probably are not physical, but I looked at the most massive clumps, and I hope that they might be physical. But the best test would be to test this with a different code. So skipping this, we all know what G2 is. This is, or we don't know. We know how it looks like right now. I'm sorry, that was not on purpose. Okay, so going back to the clumps, I used a group finding algorithm in my simulation called HOP. It's also available in Amuse. And to find basically for each of my time steps, find my clumps and look at their properties. And here I plotted the properties of the clump as mass and density, and the little blue cross there is G2. So I wanted to see, do I produce G2-like objects? And the answer is yes, I do. And this is a different snapshots of time. So there's tons of those guys who look like G2. Then I filtered, do they survive over the time, and so on. And then the most important part was, do they come close enough to the black hole, so as G2 did? So I looked at some of their orbits, and the answer is yes. Some of them come actually pretty close, and I think G2 was 100, 200 AU, something like that. And you see some of our clumps came close enough to the black hole. About 3 Earth masses.
But they're too hot, right?
Yeah, they might be too hot. Yeah, I didn't really. I think I looked at density and mass together, but basically that's one of the clumps going very close to the black hole. That.
Softening length in your simulations because the clumping in SPH is very sensitive to that.
There was a dynamical softening length, but I'm not 100% sure of the perfect details of it. I just know it was dynamical. Yeah.
I think almost as interesting as the
Yeah.
So maybe another way to ask that question related is how many SPH particles were in each of your clumps, and how did you confirm that you're resolving them hydrodynamically?
Yeah, that's a very good question. And I stopped working on the clumps. What we should have done is running it with different resolutions and then see if the clumps are still there or not, and things like that.
Roughly how many particles do you recall?
I don't think. Yeah, about, I don't know, up to 1,000, I don't know.
1,000 per clump?
Yes, the highest mass clumps, I think. Yeah.
I think it's also interesting to ask, I mean, the gas in this region, there's a lot of structure, so how much of the gas that's in this region can be explained from the winds of these stars?
Yeah.
You see a lot of these.
Yeah, those arcs and those shocks. Yeah, that's true. Yeah.
Let me make a suggestion. I think, if I understood you correctly, you used outflow and boundary conditions
Yeah.
on your spherical volume.
Mhm.
Okay.
Mhm.
Which is the equivalent of zero pressure at the boundary. Okay, zero external pressure.
Yeah.
In fact, the surrounding galaxy is producing some pressure around the boundary.
Absolutely. Yes. Yeah.
So if you did a finite pressure gas buildup within the center.
Yeah.
And you will end up accreting much more.
Yeah. Also, there's much more stars outside the S stars. There's actually Wolf-Rayet stars, which put stuff in there as well.
What I'm saying is that's what's producing the boundary. So you can do it with your volume, it's all right. But you have to have a boundary pressure.
Yeah.
And you might produce orders of magnitude more efficient.
Yeah, that's true. But I also think there is some colder gas flowing in from the winds of the Wolf-Rayet stars, which was actually also a plan we wanted to do. With Jorge Cuadra was simulating those Wolf-Rayet stars, and we would like to combine that, maybe get their boundary conditions of the gas flowing in. But yeah, that project finished didn't finish before I actually went to do JWST stuff. So that's why I got a little bit plunged. Okay, so we still have 5 minutes to catch the shuttle. So let me quickly conclude. We used AMUSE to combine physics, gravitational dynamics, stellar evolution, hydrodynamics, and we tested that with the S stars to see the accretion of the stellar winds onto the black hole. And those are just some results from the paper that you can look up. So basically that we found that the S stars alone are not responsible. At least in our simulations, we couldn't completely explain it. And in the future, we have actually, so one of the good things for working for JWST, we have GTO time to look at the galactic center with the 2 IFUs we have on it. And we hopefully can also pinpoint down a bit more the masses and the stellar parameters, similar what Stefan was doing to give them individual masses. Sorry.